So on top of the sine and cosine trigonometric functions, there are some other trigonometric functions that come from that sine and cosine, and that's what we'll explore in this section. So before we can take a look at the graph of the tangent function on an xy axis, we need to come up with some ordered pairs that we can plot. So we will take a look at inputs, which are angles, and outputs. And the outputs for the tangent function come from the ratio of the sine function to the cosine function. And we'll use a unit circle to help us out here. So when we have an angle measure of negative pi over 2, so remember negative pi over 2 is starting on the positive x-axis and it moves clockwise. So negative pi over 2 is in the same position as 3 pi over 2. We can say that the tangent of negative pi over 2 is equal to the sine of negative pi over 2 divided by the cosine of negative pi over 2. Well, the sine of negative pi over 2 is negative 1, and the cosine is 0. And negative 1 divided by 0 is undefined. So that gives us the ordered pair negative pi over 2 with an undefined output. For negative pi over 3 is in the same location as 5 pi over 3. And we see that the sine is negative square root of 3 over 2. And we're going to divide that by the cosine of negative pi over 3, which is 1/2. Squeezing that in there. And when I do that division, I end up with negative square root of 3. So I have the ordered pair negative pi over 3, comma, negative square root of 3. Negative pi over 4 is in the same location as 7 pi over 4. The sine of negative pi over 4 is negative square root of 2 over 2, and I'll be dividing that by positive square root of 2 over 2. So that output, where they are the same values, but one is positive and one is negative, ends up with a negative 1 value. So I have the ordered pair negative pi over 4, comma, negative 1. All right, so now we're back to 0 and the positive numbers. The tangent of 0 radians is equal to the sine of 0 radians, which is 0, divided by the cosine of 0 radians, which is 1. And 0 divided by 1 is 0. So we have an ordered pair that looks like it's at the origin. For pi over 4, the tangent of pi over 4, we know that the sine and the cosine are the same, and so that output is 1. That gives us the ordered pair pi over 4, comma 1. For pi over 3, the tangent of pi over 3 is going to be the sine of pi over 3, which is the square root of 3 over 2, and we're going to divide that by the cosine, which is 1/2. Looks a lot like negative pi over 3, doesn't it? Only difference here is it's going to be positive. So I'm going to have the ordered pair pi over 3, comma, square root of 3. And finally, we'll end up at pi over 2, where the tangent of pi over 2 is going to be positive 1 over 0, and that gives us another undefined output. All right, so now let's plot those points. And what's a little strange here is that we have outputs that are undefined. So for example, this first point, negative pi over 2, comma, undefined, I can't plot that. All that I know is that at negative pi over 2, at this input of negative pi over 2, there are no outputs. There are no places on this output area that I can plot anything. You might remember that from previous classes as what we call an asymptote. This will be a vertical asymptote. And we have one not only at negative pi over 2, but it looks like we're also going to have one at positive pi over 2. So let me just go ahead and mark those in. All right, now let's plot some other values. Negative pi over 3, comma, negative square root of 3. It might help to know that square root of 3 is approximately 1.73. So I'm going to plot the point negative pi over 3, comma, negative 1.73. And that is going to be around right here. So I'm going to the left pi over 3, and then I'm going down 1.73. All right, so I took care of that point. The next point is negative pi over 4, comma, negative 1. Now, negative pi over 4 is not listed on my horizontal axis, but what I know is that negative pi over 4 is going to be between negative pi over 3 and negative pi over 6. And so I'm going to go there and then go down to negative 1. 0, 0, of course, is the origin. Pi over 4, comma 1. Pi over 4 is between pi over 6 and pi over 3. So I'm going to go up to 1. And then finally, pi over 3, comma, square root of 3. That is going to be pi over 3, comma, positive 1.73. And so let me go ahead and mark that on there. And if I connect those points with a smooth curve, I get something that looks like that. Now, does it stop there? No, it keeps going, and it actually keeps going and gets closer and closer and closer to what we called that vertical asymptote. A vertical asymptote, or even a horizontal asymptote, but a vertical asymptote, how that's defined is this sort of imaginary line that a curve gets closer and closer and closer to. Now, if I could pick this picture up and stamp it on the right and stamp it on the left, I would see more, more of this graph. So even though it looks like, that's not very straight. Even though it looks like these are 3 separate pictures, these 3 images actually make up the full graph of the tangent function. The one period was what we graphed in this table. So that's one period. So a couple things to notice. From 0 to pi over 2, from 0 to pi over 2, right? What was happening there? The tangent values were increasing, weren't they? They were increasing. And from 0 to negative pi over 2, from 0 to negative pi over 2, they are decreasing. They are decreasing. And then the only other thing to say, or just to formalize here, is that we've seen that this tangent function has vertical asymptotes. Now that we've looked at the graph of the tangent function, we can use that graph to try and derive a graph of the cotangent function. Before we do that, however, let's answer this question. When does the tangent function have a vertical asymptote? And can we wrap our brains around why that's happening? Well, we saw in the last slide that the tangent function has vertical asymptotes at, it looked like, negative pi over 2 and also pi over 2. In this picture, we can see also that it appears at negative 3 pi over 2 and positive 3 pi over 2. Now, when we came up with those values in the table of values, we used the relationship that we know about the tangent function to say that the tangent function is equal to the sine of the angle over the cosine of the angle. So in that function, when that denominator, in this case the cosine, when that denominator was equal to 0, we saw that the tangent function was undefined. So to answer the question, when does the tangent function have a vertical asymptote? Well, the tangent function has a vertical asymptote when its denominator is equal to 0. So in the tangent of theta equals sine over cosine, when the cosine of theta is equal to 0, we will have a vertical asymptote. And again, that is because we cannot divide by 0. So when you have 0 in your denominator, that's when you get something undefined. Now, let's take a look at the cotangent function. Here's what the graph looks like. So in this case, notice a couple of things. First off, notice that just like the tangent function, this one also has vertical asymptotes. When does this one have vertical asymptotes? Well, let's take a good look at this. So the dashed line is the cotangent function. And let me start at the origin. It looks like at 0, so I'm just going to draw a sketched line here. At 0 and at pi, and let's see, where else? Negative pi. That's where this function, right? That's where this function is approaching, but not quite reaching. Okay, now why is that happening? Well, let's remember what a cotangent function is. Cotangent is the reciprocal of the tangent function. So that means that the cotangent is equal to the cosine of the angle over the sine of an angle. So in the cotangent relationship, same thing as we saw with tangent, but now sine is in the denominator. So when the sine of an angle is equal to 0, we should expect to see vertical asymptotes. Now, I'll leave it up to you to confirm what angle does produce a sine of 0. I'm going to guess that the answer to that is negative pi, 0, and pi. So now let's take a look at the graph of the cosecant function. We've done tangent and we've done cotangent. Now let's look at cosecant. Now, because the cosecant function is the reciprocal of the sine function, it might be expected that there is a relationship between the two graphs. So let's take a look at those two graphs. We have the sine function. We've seen that before. This is what the cosecant function looks like. And notice that unlike the sine function, the cosecant function does have vertical asymptotes, doesn't it? It looks like a bunch of individual graphs, but in fact, all of those dashed lines make up the cosecant function. So what we can say is that the cosecant function has vertical asymptotes at, it looks like negative pi, right? Negative pi. Looks like also at 0, an x value of 0, or an input value of 0. Also at pi. And of course, that's just what I can see on this picture, but that's where it appears that that's happening. So why is that happening? Well, we're going to go back to how we have defined the cosecant function. The cosecant of an angle is the reciprocal of the sine function. So that's 1 over the sine of theta. So when that denominator, when the sine of theta is equal to 0, then we have a cosecant that's undefined. The cosecant will be undefined. And when that cosecant is undefined, so when the sine of theta is equal to 0, the cosecant is undefined, then that means that there are vertical asymptotes. We can't graph something that is undefined. So make sure you've got a unit circle next to you. I'm going to sketch in a really small one up here. If you think about the circle, what angle produces a sine of 0? Well, I know that along the positive x-axis, that's an ordered pair of 1, 0. That is a sine of 0. Up at 90 degrees, I have the ordered pair 0, 1. That's a sine of 1, so that wouldn't be a problem. We're going to see the problem again when we get over to pi. That's going to be at negative 1, 0. So that's why we see the issue at pi, we see the issue at 0, and of course I could also go to negative pi, which is simply at the same location as pi. All right, and the last graph for us to look at is the graph of the secant function, and you've probably got the hang of this at this point, but because the secant function is the reciprocal of the cosine function, there is a relationship here as well. The cosine function, we've seen that before. That's what the cosine function looks like. Here is the graph of the secant function. Notice that we do have vertical asymptotes. Looks like the vertical asymptotes, where are those happening? Looks like at negative 3 pi over 2, at negative pi over 2, at positive pi over 2, and at 3 pi over 2. Why are those vertical asymptotes occurring at those values? Well, it's because the secant function comes from the reciprocal of the cosine function, right? Comes from that reciprocal. So when the cosine of an angle is equal to 0 for the secant function, that means that it's undefined. So when the cosine of theta is equal to 0, the secant will be undefined. And if the secant is undefined, then we have vertical asymptotes. Now, I drew a little circle on the last slide to talk about where was the sine of a function equal to 0. We could do the same thing for the cosine, but I'm gonna say that if you have it memorized, you might say, okay, well, why is it pi over 2? Why is it pi over 2? Well, that's because the cosine of pi over 2 is equal to 0. And so 1 over 0 is undefined, and that's what's not allowing us to put any points along that line through pi over 2, and that's what's giving us the vertical asymptotes. So now that we've looked at all of the different types of functions, let's do some summary. The first summary is of the domain and range of the tangent function. And we looked at this picture, and we can say now that the domain of the tangent function is all real numbers, except, of course, for anything that makes the cosine equal to 0. That's what created that undefined value and gave us the vertical asymptotes. That's occurring at odd integer values of multiples of pi over 2 or 90 degrees. Now, why odd integer multiples of pi over 2? Well, because we're seeing a vertical asymptote at 1 pi over 2, and then we saw it again at 3 pi over 2. 1 and 3 are both odd numbers. An even integer multiple of pi over 2 could include 2 pi over 2, which is pi. And we see in the graph that at pi, we actually have an output. We don't have a vertical asymptote. So that's why we're saying odd integer multiples. The range of the tangent function is all real numbers. These curves go indefinitely to positive and negative infinity. Now let's look at the cotangent function. The cotangent function is the dashed line, and we can say that the domain of this function is also all real numbers, except for where we see the vertical asymptotes. And we saw the vertical asymptotes, looks like through the line that goes through 0, through the line that went through pi, through the line that went through negative pi. That's for the dashed line. Don't confuse it with the other one. So 0 pi, 1 pi, I bet we could even say 2 pi. So these are just integer multiples, not odd integer multiples. And we're going to say that that's of pi or 180 degrees. And this one has a range that is the same as the tangent function, being all real numbers. Now let's do a summary of the domain and range of the cosecant function. The domain of the cosecant function includes all real numbers except integer multiples of. So we see the cosecant function in the dashed line, and we can see that there's vertical asymptotes that appear to be from the left at negative pi, looks like at 0, and it looks also like pi. So it looks like multiples of pi. And we don't have to say odd multiples of pi because it's at 0 pi, 1 pi, 2 pi, 3 pi, so any integer multiple of pi. The range of the cosecant function is also all real numbers, but you might have noticed that there is a break in this graph from 1 to -1. We don't see anything graphed in the range of the cosecant function along this middle strip. And so that's why we limit the range of the cosecant function from -infinity to -1, closed bracket, unioned with closed bracket 1 to +infinity. That's just a formal way of saying all real numbers except for the space between -1 and +1. Now let's take a look at the domain and range of the secant function and summarize some findings. The domain of the secant function is all real numbers, and we can see that the exception to that are at the vertical asymptotes. And I see a vertical asymptote on the left at -1 pi over 2. I see another vertical asymptote at +1 pi over 2. 2 pi over 2 would actually be pi, and there is no vertical asymptote there. So that's why this definition is all real numbers except for odd integer multiples of pi over 2 or 90 degrees. The range of the secant function is similar to that of the cosecant function that we just saw, in that it is all real numbers except for this band between -1 and +1, where there is no range of the secant function.